to enhanced thermal structural analysis using reduced order modeling, to be presented by Derek Hengeveld. I hope I got that name right.
Well, that sounded great. Great. Yeah, thanks everybody. I really appreciate the time to talk over this research. The title of this talk is Enhanced Thermal Structural Analysis Using Reduced Order Modeling. Before I jump into this, I do want to acknowledge the co-authors, Jacob Moulton and Ryan Vasses from Redwire, and then also from NASA Goddard, Alice Liu, and Hume Peabody. This work that I'm covering today was based on a NASA SBIR Phase 1 program, so certainly want to acknowledge NASA's sponsorship. All right, so if you're somewhat familiar with what we've done in the past, we've built up a reduced order modeling tool set for thermal applications. And I'll, in the next couple slides, I'll just give a real brief overview of what that looks like, how it works. But I think what you'll find is that the approach that we're taking is very, very robust, meaning that it can really be applied to a number of different applications. And so what this talk is basically looking at that. How can we extend our existing reduced order modeling software to other applications? And so we picked thermal structural applications. We at Redwire, we do a lot of that type of work. And it's certainly a type of work that's of interest. You know, if you're a person that might be interested in thermally induced deformations, this is kind of geared towards that. All right, so just a couple slides just on the background. So as I mentioned, we have developed tools for creating reduced order models for high fidelity thermal models. So you start with a high fidelity thermal model. We have this software tool called Veritrek that basically allows you to convert that thermal model, specifically a thermal desktop model, into a reduced order form. And you might be wondering, well, you know, why do we want to do that? The main motivation is that we can run simulations very quickly, where a typical high fidelity thermal desktop model might take minutes to hours, maybe days to run a single simulation. By converting it first to a reduced order form, we can then run thousands of simulations in just seconds. I'm just going to show a quick demo of what that looks like. This is a kind of the end of all of this. This is, we took a thermal desktop model for the NASA Crew Exploration Vehicle. This is some work that we did with NASA Johnson a number of years ago. We converted that into a reduced order form and then pulled it into our software tool. What we're seeing in the middle here is a user is then interrogating that reduced order model. Again, this is a reduced order thermal model, and changing input factors to that reduced order model. This particular model, this particular thermal model, had inputs such as heat loads, and it had a fluid system. So there's a regenerator component to it, different working fluids that we can change. And essentially what's happening behind the scenes is that every time the user is changing the input factor, moving those sliders, we're running 400 reduced order model simulations in the background to generate the response surface on the right-hand side. And you can see that things are essentially updating in near real time. This is not something that you could do with traditional thermal modeling methods. Again, if you're trying to run 400 simulations to generate this response surface, and each of those simulations takes minutes to hours to days to run, it's just not computationally tractable. But by first converting the thermal model into reduced order form, we certainly can do that. So this is just to kind of give you an idea of what we're dealing with here. All right, so the current form of the tool has been used by a number of folks. You kind of have some examples there in the bottom left. A number of different NASA centers, NASA Goddard on their LRALPH program, and their Exclaim program. Momentus has used it recently, Sierra Space on their Dream Chaser program. Ball Aerospace used it for some cryogenic thermal model correlation. And then also of note would be the NASA JPL's Mars 2020 helicopter program. They used reduced order thermal models to help with not only the design of the helicopter, but also in mission planning. One of the key components to this talk is how we're generating the reduced order models. And so I have a very simple example on the lower left to kind of illustrate how we're going from a high fidelity thermal desktop model into a reduced order form that we can run, thousands of simulations in a few seconds. In a number of cases, folks basically take high fidelity models and they reduce node counts. That's not what we're doing. We're essentially just sampling and data fitting from that high fidelity model. So just as an example, let's assume you have a thermal desktop model and you want to understand the relationship between an input factor, let's say a heat load, and then an output response, let's say temperature. What you might do is you might go ahead and run that thermal model at a number of different input factor settings. So let's say 0 all the way up to 5 watts. And what you're going to do is you're going to run 6 different cases. A case at 0 watt, 1 watt, 2 watts, et cetera, et cetera. And you're going to track the temperature output response. And what we end up with is this data shown by these red circles. This, in our view, this would be considered training data for our model. And so the next logical step is, hey, we have this data available to us. Let's do a data fit and come up with an equation that describes that relationship between this input factor and output response. And so that's what we do. It's very linear, nice and easy to generate this equation, y equals 10x plus 10. And so let's say sometime later, someone comes up to you and asks, well, what's the output response? What's the temperature if my heat load is at 3.5 watts? Well, we haven't sampled that before, and we certainly could go back and we could run our thermal desktop model to get that result. But something that's that's going to be faster will just be use this model that we've already developed. Put in 3.5 in for X, out comes 45 for Y. And that's essentially what we're doing with this approach. We're sampling. So determining of these input factors, what points do we want to sample at, generate this training data, and then generate this model that we can then use very quickly. Except with what we're doing, we're expanding that quite a bit. This is a nice 2D example, something that I can show on a PowerPoint slide. What we're doing with the thermal reduced order modeling is we're dealing with multiple input factors. I think the highest number of input factors customers use to date is, I think, 39. And then output responses, we're not just dealing with a single output response, we're dealing with multiple. And I think our maximum customer use case is, I think, around 90 or so output responses. And not all temperature output responses. You can have things like maybe a heater value. Anything, if you're a thermal desktop user, anything you can track with a register, we can certainly capture here. And really what the tool does well is that it does the sampling very well. It samples enough so we get good enough accuracy. And then it also does a really nice job of data fitting. All right, so how can we use this type of approach? Well, again, if we have this reduced order modeling approach that allows us to have thousands of simulations in seconds, we can do things like uncertainty quantification or rapid thermal model correlation or screening studies or optimization studies, types of analyses that really weren't accessible to us in the past. All right, so with that, kind of the preamble to all of this, hopefully you can see that the approach that we're taking, sampling and data fitting, could really be universally applied to a number of different applications, not just thermal, but perhaps thermal structural. And so that's the direction that we went on this SBIR phase 1, is what would that look like if we applied our reduced order modeling to those types of problems. And so we started with this simple case study. This one was a simple bracket, which we can see in the upper right. This bracket the geometry was built up in SolidWorks, and then we did a structural analysis in Nastran, and again, the thermal analysis in Thermal Desktop. For this particular reduced order model, we had 4 input factors. So we put this bracket in space, and we had a pitch and a yaw input factor. We can vary the pitch and the yaw by 0 to 90 and 0 to 45 degrees respectively. We also had an applied load, and we could apply that load in both the minus X and minus Y from 0 to 100 pounds force. And then we also were tracking 3 output responses. And essentially what we were tracking is this deformation at this output node. So deformation in the X, Y, and Z, indicated by U sub X, U sub Y, and U sub Z. This just kind of shows the workflow that we took. Again, we started with a common geometry. That geometry is pulled into a thermal desktop model. And then that geometry was also pulled into a Nastran model. Our inputs to the thermal desktop model were pitch and yaw. We changed that. And then the outputs of the thermal desktop model were temperature maps that we then brought into the Nastran model. And then coming out of that Nastran model were the deformation outputs. All right, so let's just take a look at some of the results of this first effort. Again, a nice simple case study. What we did is we ran 32 training data points. If you recall from that initial very simple example with the red circles, essentially 32 points that covered the input design space. We also had 12 test points. And so we took those 32 training data points and we used that to develop the reduced order model. And we can see the training results here on the upper left and lower left. What this shows is the reduced order model predictions against the training data, or essentially the truth results. And we would certainly expect that these values should be in perfect agreement, meaning that our model perfectly matches the truth results to the reduced order model results. And we see that here. They fall on a 45-degree line, meaning that the reduced order model and the truth results are in perfect agreement. Did a couple parametric sweeps just to kind of further prove that. These solid lines are the reduced order models that were developed, and the dots here are the training data points. Then we took that reduced order model and we compared it to test results. So these test points weren't used in generating the reduced order model, but they're merely there to see how good that reduced order model does. And we're going to start to see a little bit of noise. So here on the upper right, we see the reduced order model compared to the test data across all 12 test points. We see a little bit of noise there. They're not falling on a perfect 45, maybe slightly off. And that's to be expected. The reduced order model at non-training data points won't perfectly replicate these test points. And we did the same thing down here with these parametric sweeps. And again, we see a little bit of disagreement between the ROM and the truth results. But essentially, overall, we saw this, we saw the results, we went through the process of getting from both a thermal and a structural model into a ROM that we could use, and we were encouraged. And we wanted to move on to a more difficult problem, so we reached out to our friends at NASA, and they certainly gave us something much more challenging than our simple bracket. We're actually dealing with the Roman Space Telescope. They were kind enough to allow us to use the Roman Space Telescope thermal desktop model, and then also provided structural results from that model too. This particular thermal model is a roughly 50,000 node thermal desktop model. And so there were some more complexities in just data flow. So we built up a series of different tools to basically get us from thermal inputs and structural inputs into a reduced order model. Some of that was dealing with a interpretation file, and we built up a C# conversion tool to allow us to work with that. But essentially the process that we saw before was very much the same. We're dealing with thermal inputs. We're taking those thermal inputs to map the temperature to the structural model, and then from the structural model, we're getting distortions. All right, so let's just take a look at the input factors. We had three input factors, hot and cold cases on the thermal model, and both X and Y pointing. And we can see the ranges of these different pointings that we had on the thermal model. We had 42 output responses. So we had 7 node locations that we were looking at. And these are the node numbers here, not very interesting, but we did have 7 nodes that we were looking at. And at each of these nodes, we were looking at both X, Y, and Z deformations and X, Y, and Z rotations at each of those locations. So again, 3 input factors, 42 output responses. Let's take a look at some of the results of this. Okay, on the left-hand side here, we have the training results. Again, we would expect to see perfect agreement between the developed reduced order model and the truth results, and we do see that. This was developed based on the reduced order model was based on 9 training data points. And we see, again, perfect agreement on this top left plot, and then perfect agreement on the bottom left plot. But as we go to the test results, we have 3 test points. We see a little bit of noise as we saw before, and then we see a couple spots where the outputs are deviating more significantly. In particular, this hot UZ, so this Z displacement result did deviate quite a bit. Kind of the fix for this type of thing would be, hey, let's throw more training data points at this to kind of tighten that up. But with this, we were pretty satisfied with the overall results. Certainly not that point in itself, but overall, things look pretty good for us. And so we wanted to demonstrate how we could use this ROM. So again, at this point, we've developed a ROM, we've tested it, we felt good enough about the test results that, hey, let's see how we could use that. All right, so now here's where we're getting into the power of the reduced order model. What we wanted to do to kind of demonstrate how you potentially could use thermal structural reduced order models is what would happen if we wanted to look at, let's say, some uncertain input and how that impacts the output of interest. And so what we assumed is that we had a uncertain input distribution on the pointing angles. So again, we had X and Y pointing angles. And so we gave both the X and Y pointing angles essentially a Gaussian distribution. You can see those distributions here, and we basically flowed that through the reduced order model. We sampled from each of these distributions, and we essentially threw 10 million samples at this to generate these output distributions. So basically what this says is that if our pointing angle, X and Y pointing angle distributions were of this shape, these are the output distributions that we'd expect for both X, Y, and Z deformations and rotations. So you can start to see some of the new capabilities that you would be able to get with thermal structural reduced order modeling. This is something that's probably not been done, but certainly something of value. Now you can assign probabilities to given deformations or outputs of interest. All right, so one last slide here before I wrap things up. We did do a structural only evaluation of this approach. This is some work that we did with a commercial customer, and they essentially put together a structural platform. What you can just imagine that this is a deck inside an aircraft. We have a couple chairs sitting on that deck, and what we did is we basically had 3 different types of input factors. One was the deck itself, which we can see here, and it's split up into 3 different areas, 1, 2, and 3. And then we have X ribs, so ribs along the X. This is the underside of this structural platform. And then Y ribs. And we're varying the thickness of the deck, varying the thickness of the X ribs, and varying the thickness of the Y ribs, both at 3 different locations. So the deck is at three sections, and the X ribs, again, 3 sections, and the Y ribs, same thing. So we essentially had 9 input factors, and then also 2 output responses. What we were trying to track, I should mention that we had point masses on top of these chairs, and what we were trying to evaluate were the outputs of mass and von Mises stresses. And so we basically took all of this, we did a little over 1,100 simulations. Most of that was training data points, part of that was validation points, and then some test points. We went through the process of generating the reduced order model, testing that model. Take my word for it. The ROM for this particular application looked really good. We had a nice agreement against test points. And then we just ran a couple of different analysis cases to kind of see, hey, what could we do with this ROM? Again, trying to leverage the speed of the reduced order model. And on the left-hand side, we did essentially an optimization analysis where we're just basically just covering these input factor ranges. So the deck, the X rib, and the Y rib thicknesses were varying from 0.03 to 0.3 inches. And we're looking at, hey, what's the optimal front? We're trying to minimize stress and minimize mass. And so we kind of come up with this Pareto front down here where stress is minimized and so is mass. And then from this Pareto front, we probably want to figure out, hey, where best would we want to have our design located. Another thing that we're able to quickly do, again, just leveraging the speed of a ROM, is looking at sensitivity analyses. So given our maximum stress, what's the biggest driver to that stress? And we have a screening analyses or sensitivity analyses that allow us to very quickly look at that. And what we found is that the thickness of deck 3, right underneath these chairs, is the most significant player on maximum stress. So the thicker we can make that, the better. The thickness of deck 2 is kind of next up, and then thickness of rib X3. So X3 on this side over here would be the next biggest contributor to the maximum stress. So here we now can start to optimize the thicknesses of our deck and our ribs to minimize mass, minimize stress, and we didn't include it here, but potentially minimize cost. All right, so just wrapping things up, we expanded our reduced order modeling approach to include structural analyses. We initially, under this SIVR program, we were hoping to go initially just looking at thermal structural applications and eventually looking at thermal structural optical applications. We're not to that point yet, but we've certainly looked at thermal structural analyses, and hopefully you've kind of seen some of the benefit of this approach. We can do rapid simulations, which really opens up the type of analyses that we can do. We can evaluate uncertainties. We can look at more optimal solutions, recognize critical design inputs. And with that, I just want to acknowledge NASA for their support on this, and special thanks to Michael Ackerman at NASA Goddard. He did a lot of work on the structural analysis for this SBIR Phase 1 program. So I appreciate everybody's time, and I'm happy to answer any questions.
All right, thank you for that talk. We have a couple of questions in chat, and I think we have time to address them. First question, what is the Python reduced order modeling tool compared to the Veritrack software?
Yeah, great question, Joseph. Yeah, pretty much the same thing. It's the same. So the engine that was used for this work was the same engine that we're using for Veritrack.
And our next question, would there be any assumptions such as linear, small deformations, etc., while creating a reduced order model?
Really, whatever assumptions you're making for the high fidelity model, whether that's the Nastran model or the thermal desktop model. The reduced order model, as you can see from the approach that we're taking, sampling and data fitting, it just captures whatever assumptions that you're using for your high fidelity model. I think that's one of the advantages of the approach that we're taking, is that we're really trying to capture what your inputs into the high fidelity model. So, if you are making those assumptions in your high fidelity model, that will be captured in the reduced order model. Hopefully I answered that question. Yeah.
I had one question of my own. So the software seems to follow a design of experiments methodology. When setting up one of these, how much does the user need to intelligently select factors and sampling points to be able to determine where there might be nonlinear effects or important interactions? And how much does the software kind of guide them through that process?
Yeah, that's a great point. For what we've developed so far with Veritrack, which is just a thermal reduced order modeling tool, the creation tool, which is the tool that converts your thermal model into a reduced order form, that tool kind of walks you through that process. So it's very semi-automated, but it allows you as a user to do that at your own computer. The process of getting from setting that up is maybe 20 minutes to 30 minutes to set your input factors, your number of sampling points, and then the tool does all the heavy lifting for you. For the work that we presented here on the thermal structural, since that framework wasn't included, we had to set up a number of different tools here. That was a little bit more manual, but it's certainly something that if there's a lot of interest in thermal structural reduced order modeling, our plan is to pull this type of work into our existing software tool.